So I've already showed you the classic hydrohalogenation reaction, and I didn't tell you what the solvent was, but we will assume it was some non-nucleophilic solvent, something that doesn't get involved. And an example here might be dichloromethane. And so it's not going to be participating in the reaction. So the idea was that you have a terminal double bond which reacts with HBr, adds H to the primary position, adds Br racemically to the secondary carbocation. This proceeds via a Markovnikov pathway, and those are the products I've already shown you. Now, if you are used to trying to memorize things, and then you go to this point of the semester in organic chemistry, all of a sudden I can ask you an enormous swath of problems that you simply would have to memorize them all if you were trying to categorize them by the reagents over the arrows, or just simply memorize your way past them. But if you're thinking mechanistically, then all of the problems that I've drawn so far on this board are fundamentally the same, and you can now solve all of them because I've told you the mechanism of how this works. There's no mystery here. You can figure this all out based on the mechanism. But if instead what you're trying to do is memorize things, then this is a different set of conditions than those. Will you lead to the same product? Yes or no? Why? And you really don't have any way of figuring it out unless you're thinking mechanistically, and then you'll find your way to the right products almost immediately. Likewise, this is a totally new situation, totally different acid, totally different solvent. What do you make? Well, thinking mechanistically, it's actually the same problem. Trying to memorize, it's totally different. What do you do in this situation where there's two double bonds? How do you figure that out? Again, mechanistically, it's going to behave exactly the same way, except of course now you have a little bit more nuance because there's going to be a resonance stabilized carbocation which then gets attacked. Is this more complicated? You bet. But all of these problems are fundamentally the same from a mechanistic understanding, which is why I'm focusing so heavily on teaching you the mechanisms. If you understand the mechanisms, they're all the same problem. If you're not thinking mechanistically, they're all totally different and you need to memorize each one. And so the amount of stuff that you need to memorize from this point forward just explodes unless you understand mechanisms. And then you're really doing one thing again and again and again. And again, my one trick for how to make your life easier when it comes to mechanisms is just simply draw everything out in Lewis structure form. So if you're going to have an HBr, don't draw it as HBr. Instead, draw it as H bond Br with the lone pairs. Draw methanol as methyl dash oxygen, 2 lone pairs dash H, and so on. Because once you draw these things out and you see the explicit hydrogens and you see the lone pairs, it will help you categorize things. Methanol is a nucleophilic solvent, but it also has an electrophilic hydrogen, and so on. You can start to think about these things once you see them all drawn out. But in any event, the double bond is going to serve as the nucleophilic partner in the first step. So you're going to take the pair of electrons there, and it's kicking the pair of electrons onto the bromine. Again, you want to think of these electrons as really being part of the primary carbon when you draw this arrow. So you're really making a bond between the primary carbon and the hydrogen, not the secondary, because you want to put the plus on the secondary. This is going to lead to a cation at the secondary position, as just mentioned. It's also going to lead to Br minus floating around at this stage. So what could we make? Well, according to what we already discussed above, the bromine could now come in and add. And again, if you don't see that immediately, then draw the lone pairs on the bromine, and now you recognize that the bromine is a nucleophile because it's got a lone pairs. The lone pair does the attack. One of the products that you make is going to be the same as above, of course, and that's because if you have HBr around, then the Br is a nucleophile. It can add to the secondary, and you get this racemic product. So far, so good. However, the other thing that can happen at this stage could interfere is that the methanol is a nucleophile. Is it a particularly good nucleophile? No, not particularly, but it is present in huge amounts because it is the solvent for your reaction. It's the thing under the arrow, which means you have a lot of it. And even if it's not as good of a nucleophile, well, then it can still get involved. And so at this stage, what you now have is a mixture of two potential products, one where it's up, one where it's down. Again, we got the squiggle, and it's the protonated ether product. So what happens at this stage? Well, you have more methanol because it's just floating around in there. The methanol comes in and removes that proton, and so the final product that you make here is just simply the methyl ether product. And again, you're making both potential methyl ethers. And so really, mechanistically, it's the same. This attacks, you get a secondary carbocation, the bromine could add, which would give you the product that you expected, and that part's fine. But if you wanted to make all of that product, you'd be using some non-nucleophilic solvent like DCM, so it couldn't get involved. If instead you are throwing in some methanol, presumably it's because you want it to participate in the reaction. And therefore, the methanol goes ahead and attacks, and the H then gets deprotonated, and then you lead to the product observed. Keep in mind, again, that if you want this reaction to take place, that you really shouldn't be using much HBr. You should have very little HBr, maybe catalytic HBr, and lots of methanol. But of course, if you really wanted this reaction to take place, why would you use HBr at all? Why not use something that's a source of H+, but that doesn't have a nucleophilic bromine? So you could use sulfuric acid as your acid if you wanted that to happen. And so drawing out its Lewis structure, again, you would have the pair of electrons really being localized on the primary carbon when it goes to do this addition, so that then you put the secondary carbocation carbocation, because that's going to be the more stable carbocation. In other words, you're going to form something that looks like that. You now have hydrogen sulfate floating around, but that's not nucleophilic. What is nucleophilic is the water, so maybe the water comes and adds instead, which leads to this protonated alcohol intermediate. But of course, you could invoke another molecule of water if you wanted, so another molecule of water comes by and pulls off that proton, and your final product is going to be just the alcohol. And again, mechanistically, it's nearly identical to this process, with the only difference that here we had a methyl bound to the oxygen, which wasn't doing anything, and here we have an extra H bound to the oxygen that isn't doing anything. But otherwise, the mechanism for this process and the mechanism for this process are identical. And functionally, it's identical to the original mechanism here, where this just attacks an H, creates a secondary carbocation, and gets immediately trapped by the bromine. This is more complicated. We'll deal with it separately, but it won't surprise you to learn that it starts exactly the same way, and then it deviates a little bit.